Welcome to The Explainer. Today, we're jumping right into the microscopic physical reality of computers to completely shatter a massive illusion. We're going to bust the myth that artificial intelligence calculations are perfectly exact. Because, beneath all those glowing screens and the flawless-seeming text generation we use every day, there's actually a highly secretive hidden physics engine running the show. And believe it or not, it behaves a lot more like a wild casino than a pristine calculator. So let's kick things off by breaking down a foundational myth of our digital age. We all kind of assume that the machines driving our modern world deal in absolute, perfect mathematical truth, right? I mean, we intuitively feel like the computer just gets our intent and processes our prompts with flawless logic. But physically, down at the hardware level, the machine only understands resistance and voltage. That's it. And there's this brilliant quote from Kyle McLean Smith that perfectly anchors the whole problem we're looking at today. He says, "It's fundamentally an approximation system, not real arithmetic." This perfectly reveals that the physical engine driving advanced AI is, at its core, an estimation system. It's physically bound to make highly educated guesses simply to keep up with the overwhelming volume of continuous data it has to chew through. It literally is not doing real arithmetic.
And the scale of this is honestly staggering. Something like 80 to 90% of modern AI compute cycles are actually just hardware-level approximations. When these massive language models are doing their heavy lifting, they aren't calculating exact ground truth realities. They're fundamentally just guessing the nearest answer. And this creates a massive, totally invisible hardware crisis right beneath our fingertips.
Which brings us to Section 1, Meet the Antagonist, the FPU Gambler.
The specific component responsible for all this guessing is the floating point unit, or the FPU. Inside your computer's physical brain, the FPU acts like a frantic gambler, basically throwing darts blindfolded to guess complex math incredibly fast. But here's the massive catch. To achieve that blistering speed, chip manufacturers like Intel and ARM literally burn their own proprietary, completely secret mathematical C-tables directly into the physical silicon. This means your computer's approximation of a complex equation might actually be fractionally different than my computer's. Because the underlying math is quite literally a corporate trade secret, getting exact one-to-one mathematical reproducibility across different machines is physically and mathematically impossible. Experts call this phenomenon non-deterministic drift.
So mechanically, why does this drift happen? Well, continuous numbers have infinite decimals, and the FPU simply doesn't have the memory to store them all. Under a standard called IEEE 754, the hardware is forced to constantly chop off tiny fractions, like the 23rd decimal bit, just to squeeze those continuous numbers into fixed memory slots. Over billions of concurrent AI operations, these microscopic rounding errors violently compound. It's exactly like building a massive mathematical house of cards. Eventually, the whole tower is going to start to lean.
And this lack of precision leads to a devastating real-world consequence that researchers call the wood chipper effect. Let's look at how it plays out. Step 1. The AI ingests exact source data, maybe a copyrighted book or some really sensitive financial ledgers. Step 2. The FPU hardware approximates the math of that data, using those secret silicon tables we just talked about. And finally, Step 3. Because that math was just a lossy guess, the original data provenance and its exact chain of title are permanently, irreversibly shredded. Basically, the FPU acts like a giant digital blender. You might know exactly what fruits you tossed in there initially, but because the hardware uses these non-deterministic approximations, you can never, ever perfectly reverse engineer that forensic smoothie back into its exact original ingredients. The digital receipt, it's just gone forever.
Let's move to Section 2, the paradigm shift, the quantum observer paradox.
Now, here's where things get really fascinating. What if this lossy blending math isn't just a terrible hardware glitch? What if it's actually a rationally bounded, required feature of physics? To figure that out, we have to look at the deepest laws of quantum mechanics. In physics, there's a distinct split between the observer and the system being observed. But what actually is an observer? Well, the academic sources introduce this concept called the system identification algorithm. It proposes that an observer doesn't have to be a conscious human in a lab coat. No, it's simply a finite informational agent. And its ability to track an external system is strictly constrained by its own complexity budget, meaning its memory and its computing resources. And this is exactly where we hit the FPU wall.
The physical universe operates on infinite, continuous math, right? But the FPU observer only has a finite hardware register width. When the sheer complexity of what it's trying to observe totally exceeds its physical memory limits, the observer's complexity budget is completely blown. The FPU is literally forced to irreversibly erase information, collapsing a perfectly precise quantum reality into those rounded, standardized IEEE bins. It drops the trailing fractions just so it can cope with the sheer volume of data. So, the crucial takeaway here is that the FPU isn't just some broken calculator, not at all. It is intentionally bounding its distortion to manage its complexity budget. It's essentially a charitable gambler. It charitably sacrifices absolute deterministic perfection so that it can actually process the massive, continuous vector spaces of our physical universe at the literal speed of thought. All right, Section 3, the exact foil. Meet the ALU Surveyor. To truly grasp the trade-offs of this charitable gambler, we need to pit it head-to-head against the exact foil sitting right there inside our computers. On one side of a computer's physical brain, we have our chaotic dart thrower, the FPU Gambler. It's fast, highly probabilistic, and relies on totally secret silicon seed tables. But on the other side, we have the arithmetic logic unit, the ALU Surveyor. The ALU deals strictly in 100% exact, universally deterministic hardware truths. In the world of the ALU, 1 + 1 = exactly 2 every single time. Zero guessing involved. See, the Surveyor operates on a completely different reality. There are absolutely no hidden seed tables involved whatsoever. It executes on a perfect, relentless metronome of clocked voltage, where a high voltage is a 1 and a low voltage is a 0. And because it operates identically on every single CPU on Earth, it acts as a globally accountable universal witness. If you need undeniable forensic accountability and a true digital receipt, like for high-stakes enterprise systems or smart contracts, the ALU Surveyor is quite literally the only way to get it. This brings us to Section 4, Taming the Gambler, the Decode Verify Rollback Wash Cycle. So we know the Surveyor is historically slow compared to the Gambler. The big question is, how do we bridge the gap between our messy human intent and this perfect exactness without slowing modern AI down to an absolute crawl? Well, forward-thinking developers are using totally ingenious speculative scheduling frameworks like LLM-42 to build a 3-step protocol. It's called Decode, Verify, Rollback. Step 1 is decode. The AI uses the fast FPU to rapidly generate a speculative guess. Step 2 is verify. A separate mechanism takes those guesses and locks in exact mathematical parameters using fixed schedules. And step 3 is rollback. If the fast guess doesn't perfectly match the exact verification due to that floating point drift we've been talking about, the system forcefully rejects the bad data and recomputes everything deterministically. By constantly running this wash cycle, the system actively cleanses that microscopic, rounding gunk out of the FPU before it can ever corrupt the final output. It's brilliant. We can finally extract perfect precision from chaos. We get to balance the blazing, charitable speed of the FPU Gambler with the absolute, verifiable truth of the ALU Surveyor. But as we continue to offload more and more of our lives, our financial ledgers, our legal frameworks, our medical predictions onto machines, we are left with a truly profound realization. If we blindly rely on the lossy FPU Gambler to process our reality, what ultimately happens to the exact truth of human knowledge? Will you settle for the gambler's guess, letting the invisible hardware passively blur the lines of absolute truth? Or will you demand the surveyor's perfectly traceable blueprint? Keep asking the hard questions about the structures you rely on. Thanks for joining me on this explainer, and I'll catch you next time.